couple of lectures ago, I mentioned that we're going to have to go beyond a description of point masses if we're going to describe complicated real-world physical systems. And you could argue that on a microscopic level, everything's made of point masses, like even a fluid. But you'd even be wrong about that, because even at a fundamental level, you can't describe, say, a theory of electromagnetism in that way. Photons don't have any mass, and their electromagnetic field is a field. It's spread out through all of space. And so you're not going to get a theory that looks like a point mass to fit in with that. Relativistically, you also can't break down the Lagrangian into a kinetic energy minus a potential energy, even for a point mass. So we're going to have to expand our worldview on Lagrangians a little bit. We'll start by looking indeed at something involving the electric and magnetic fields. So the electric and magnetic fields can be written in a slightly more compact form because they obey Maxwell's equations. And instead of requiring two vector fields to describe it, all of electromagnetism, we can actually do with one vector field, this A vector field, and one scalar field. So we've gone from 6 numbers down to 4 for each point in space. And yet they fully specify all the legal electric and magnetic fields we can have. And what we're going to show is that this Lagrangian fully describes how a point particle, charged particle with charge q, interacts with the electric and magnetic fields. Okay, so let's look at the Euler-Lagrange equations. Or indeed, we should put this into some coordinates. I'm going to pick for coordinates Cartesian coordinates because I know exactly how everything works in Cartesian coordinates. I know how to write my kinetic energy. And I'm going to emphasize here that these scalar and vector fields depend on all of space and time. So they really do depend. So that would be r dot, I guess, and this would be a, don't forget, that's a function of r at t. Okay, so our Euler-Lagrange equation is very simple, and we can substitute in. Note that we don't have just the single r dot term, but we in fact have two. But now we have two terms that also depend on the r's. I'll take out a factor of q because it's common to both of them. Don't forget the minus sign from there as well. Let's put that over the other side. And when we take this total derivative over here, then because these r's, as the particle moves around, will depend on time, we're going to have to do a total derivative. Now this bit here has a very simple form. It's r dot cross curl of A, that's the jth component of that, which you can verify component by component, or else just look up your vector identities. And of course, curl of A is just our magnetic field, and this here is of course just our electric field. So in fact, what we have component by component is that the mass times the acceleration is precisely the electric field plus V cross the magnetic field. In other words, we've recovered the Lorentz force law from this Lagrangian.